This video is sponsored by CuriosityStream, home to over 2,500 documentaries and nonfiction titles for curious minds. This here is Euler's identity and is considered by many to be the most beautiful equation in mathematics, as it very surprisingly relates e, I, pi, 1, and 0 all together. But when you look up the second most beautiful equation, well, there's really not a specific answer. However, in one survey when a bunch of mathematicians were asked this question, many said that this was their second favorite. This here is Euler's characteristic. Well, a specific case where it equals 2. And this says that for any convex polyhedron, the vertices minus edges plus faces will always equal 2. Now, the applications of this, and really the more general equation, actually run deeper than you may think. But first, to just get a visual sense of everything, let's first look at the 5 platonic solids. A tetrahedron, for example, has 4 vertices or corners, 6 edges that connect them, and 4 faces. For the other shapes, I'll just put those values on the screen, and you'll notice that they all differ. However, when you subtract the edges from the vertices and add the faces, everything comes out to 2. And this would be the case for any convex polyhedron. In fact, even for a sphere, the Euler characteristic is 2. Which a lot of people will comment saying, what are you talking about? There's just one face, it should be 1. But consider this. If we draw great circles around here and then one around here, which I'm going to represent with rubber bands, you'll notice that there are 2 points, one here and one on the back, where the rubber bands intersect. So that's like 2 vertices. Then the edges would be what connects those. So one here, it's 2, and 3, and then one along the back, 4. So there are 4 edges. And then there are 4 faces, 1 here, 2, 3, and 4. So when we apply Euler's characteristic, the value comes out to 2 as expected. In fact, even for a globe with all the longitude and latitude lines, if you were to count the vertices, edges, and faces for the entire thing that applied Euler's characteristic, you'd again get 2. And this would always be the case no matter how you partition the sphere. So essentially, if you allow edges and faces to be curved rather than flat, Euler's characteristic holds just like it does for the convex polyhedra. So the more official rule for this is if you take something with an Euler characteristic of 2 and morph it through continuous stretching, then the Euler characteristic will still be 2. As in, the Euler characteristic is preserved under homeomorphisms. We're not allowed to poke holes or tear the object, but in general, if you can deform one shape into another continuously like they're made of clay, then the Euler characteristic will remain the same. But not every shape has an Euler characteristic of 2, like take a donut or torus. This has an Euler characteristic of 0. To see why, just like with the sphere, we can draw circles around the torus in different sections. There are 4 points where these all intersect, thus 4 vertices. There are 8 edges that connect them, and then 4 faces. Sorry if that's hard to see, but we have 2 reds on the top and 2 blues on the bottom. Then just apply the Euler characteristic and we get 0. Another way we can define the Euler characteristic is 2 minus twice the number of holes. The fact that we have an Euler characteristic of 0 means I definitely cannot morph a donut into a sphere or vice versa, because in order to do so I would have to puncture a hole or fill one in, which isn't allowed when dealing with homeomorphisms. And although Euler's characteristic began with polyhedra, it applies to flat surfaces as well. Here we can see there's 2 vertices, 1 edge, and no faces. If we add another segment, we have 3 vertices, 2 edges, and no faces. And then once we connect 2 vertices, we have 3 vertices, 3 edges, and a face. So notice that the vertices minus edges plus faces in every case is 1. However, if we claim that the outer section is also a face, like we're writing on a sphere, then all these face values go up by 1, and we have the Euler characteristic from before, which never changes no matter how many edges we draw, assuming no intersections. Okay, now we're going to move on to the applications. Pretend for a second, instead of a sphere, we're living on a giant torus, and there's a constant wind blowing around the world, which we can represent with this vector field. Ignore the cause of this, but just realize this would definitely be possible, and no matter where you are on the surface, you're going to feel that wind. But if we start to close the hole and maintain the wind, we notice something happens once it closes. We now have a 0 vector here, a place where there's no wind. But remember, this is 3-dimensional since we just closed the hole in a torus, as in we're just looking at the top view right now. But if I just squish this back to a sphere and maintain that vector field, this is what we're really looking at. You'll see that zero vector on top like we just saw, but now from this view we can see there's another one here on the bottom. So for the sphere there are 2 points where there's no wind, and for the donut there were 0. And if you remember, the donut had an Euler characteristic of 0 while the sphere was 2. I wonder if there's some relationship there. Well, there is, but it's not quite this simple. And that's because these zero vectors come in different flavors. Like there are some called centers, which is what we just saw with the sphere or closed torus, and the wind kind of spiraling into a 0 point. But there's also saddles, sources, and sinks. These aren't the only examples, but in general just realize that continuous vector fields can behave differently near their zero vectors. Now each of these vector fields has an associated index, which is not too difficult to find. To find it for the sink, let's say, just draw a circle around the zero vector and place a dial somewhere on the circle pointing in the direction of a vector at that point. We're then going to move the dial around the circle just one time counterclockwise while always having it point in the direction of the vector at its location to see what the dial does. You'll notice that it will do one counterclockwise spin during that time as shown here. One counterclockwise rotation of that dial corresponds to an index of +1. Had the dial spun around 2 times, the index would be +2 and so on. Then if we look at the source and again do the same thing with the circle and dial, you'll notice the dial will again make a single counterclockwise rotation, meaning its index value is +1 as well. And if we go to the center, again we see the same thing with one counterclockwise turn. So we've only seen indices of +1 so far. However, for the saddle, when we do the exact same thing, you'll notice this time the dial will make a single clockwise turn. And one clockwise turn corresponds to an index of -1. So in summary, of these 4 kinds of continuous vector fields with a 0 point, all but the saddle have an index value of +1. Now the reason we need to do all this is so we can understand the Poincare-Hopf theorem. This simply says, and yes I'm going to kind of oversimplify, that for a continuous vector field with isolated zeros on a surface, the sum of those indices we just saw will equal the Euler characteristic of that surface. So like for the sphere, we saw it had 2 centers, one on top and one on bottom, which each have an index of 1, and that sums to the sphere's Euler characteristic of 2. This means we could also have a sphere with a source like you see here at the North Pole. Since this has an index of +1, it means there must be at least one other zero vector somewhere though, which there is. In this case it'd be the South Pole, where we find a sink also with an index of +1. And these added together still come out to 2 as expected. So we can say that for any sphere with a continuous tangent vector field, there must be at least one zero vector. Because if there were none, then the index values would sum to 0, contradicting the Poincare-Hopf theorem. This means on Earth right now, there's at least one spot where there's no wind. It could be an extreme case like the center of a violent cyclone, but it doesn't have to be. There's a more official theorem for this, and I'm not kidding, it's called the hairy ball theorem. Yes, that's a thing. What's cool though is this was the first rigorous proof that mathematicians have a sense of humor. But really, it's just a special case of the Poincare-Hopf theorem. Instead of referring to wind, the hairy ball theorem gets its name from the fact that you can't comb the hair over a sphere without getting a cowlick, aka a zero vector, where the combed hairs can be considered tangent vectors. Also, if you do a Google search for the theorem, you'll find an old Reddit post with this picture, which isn't even on a math-related subreddit, but the top commenter does mention the theorem. Anyway, here you see the sculpture created with rocks which fit together very nicely, kind of like a smooth vector field. But we see an exception had to be made at the pole, which is like a zero vector or a cowlick. This is expected since the sculpture is spherical, and while this may not exactly reflect the theorem, you can see the similarities. Now, going back to that torus from earlier, it makes more sense now why there were no zero vectors. By the Poincare-Hopf theorem, the left side will be 0 as there are no index values to add, which corresponds to the Euler characteristic on the right of 0 for the torus. So everything checks out. But a torus could have a source and sink like you see here, with the source on top and sink on bottom. Now it was kind of difficult to draw in here, but note that by adding a source and sink, we also get 2 saddles here and here. And since those each have indices of -1, they cancel out the source and sink's indices, which are both +1, yielding a total value of 0, the Euler characteristic of the torus. And with that, we're now going to slightly shift gears to the topic of curvature. I've discussed some of this in a previous video on general relativity, but there is a lot I didn't get to. For a plane curve, the physical intuition of curvature is how much the tangent vector rotates as we move along the curve. Meaning that this straight line has 0 curvature as expected, since the tangent vector never has to turn as we move down the segment. However, for this curve, the tangent vector does turn between nearby points. Basically, if you start at some location and move the tangent vector just a little along the curve, you'll have to rotate it a little to maintain that tangency, thus there's curvature. We define this section to have positive curvature, while this section has negative curvature. Kind of like concavity, but more officially, if the curve bends in the direction of the normal vector, then that's positive curvature, and away would be negative. Now, it can be complicated to determine the value of this curvature as we need some calculus that I'm not going to go into. However, for a circle, it's easy. We just say that the curvature at any point is 1 over the radius of that circle. So when the radius is large, we get 1 over a large number, which means small curvature, which makes sense because if you walk around a very large circle, you don't curve as much. To find the total curvature of a circle, you just multiply 1 over r by the circumference, which yields 2 pi, which will always be true regardless of the size of the circle. But the cool thing is that when you deform a circle into any non-intersecting curve, the total curvature remains 2 pi. Any excess positive regions will be completely canceled out by the new negative regions, maintaining that 2 pi curvature. This also means that any polygon has a total curvature of 2 pi, since we can deform the circle into it. A polygon is flat along its edges, but carries its curvature at the vertices. And as most of you guys probably know, the external angles of any polygon will add to 360 degrees or 2 pi radians, regardless of the number of sides. So this matches that total curvature we just found. A visual way to see this is to first realize that an external angle, like A here, measures how much a car would need to turn if it drove around that corner. So if A were 60 degrees, then the car would have to turn 60 degrees to go around that corner. Then for any polygon, going around one loop corresponds to a 360 degree rotation, as the car will turn 360 degrees, or 2 pi radians, back to the original configuration. So that total curvature is kind of like how much the car will turn in total, which explains the 2 pi curvature for shapes homeomorphic to a circle, since you'll always turn through 360 degrees as you go around a single loop. So what we've seen so far is that total curvature is not determined by geometry and things like angles and lengths. It actually depends on the topology of the shape. Since these are homeomorphic to one another, they have the same topology and thus that same total curvature. But where things get more interesting is with surfaces, because now we have to deal with Gaussian curvature, which I have touched on before. In that video, I mentioned that a flat sheet of paper predictably has 0 Gaussian curvature. The reason for that though is because at any point a straight line segment does not curve at all, meaning that has 0 curvature, and the same goes for another perpendicular segment. Then when you multiply those, you get 0, of course, which is the actual Gaussian curvature at that point. The two individual segments are each the principal curvatures, but for Gaussian curvature, you're required to multiply them. So on a sphere at any point, a small segment curves outwards a little, which we say has positive curvature, and the same can be said for a perpendicular segment to that. Thus the sphere has positive Gaussian curvature at any point because it's just two positives multiplied. And for negative curvature, I use my shaver because at one point it curved outwards in one direction, but inwards when going perpendicular to that. So you get negative times positive curvature, which is negative overall. And that part brought in a few comments where people said, why didn't you just use that thing behind you? But this doesn't have negative Gaussian curvature. In fact, although it is curved, it has 0 Gaussian curvature pretty much everywhere. And that's because, yes, right here at this point, we could say it is curved, this is negative curvature. But we got to account for that perpendicular segment. And as I move perpendicular to that, it's not curving at all. So this is 0 curvature, and 0 times anything is 0. That's why this is 0 Gaussian curvature pretty much anywhere. But the thing I didn't talk about in that last video was the actual value of the Gaussian curvature of these surfaces. So like for a sphere, the value of the Gaussian curvature at any point is 1 over the radius squared. Then to find the total curvature, we can integrate over the entire surface, or really just multiply by the surface area, which gives us 4 pi, again, regardless of the size of the sphere. Okay, so now that we know that, what I've done is added a third rubber band to our soccer ball, and what you'll find is there's now a bunch of geodesic triangles along the surface. What I mean by that is, well, triangles with 3 edges, 1, 2, 3, and 3 vertices. But those edges run along geodesic curves, basically the fastest route from point A to point B, which for a sphere is always part of a great circle, or the largest circumference you can draw around the sphere. Now, there are a total of 8 of those geodesic triangles on here, 4 on the top and same on the bottom. And because we know the total curvature of this is 4 pi, then the total curvature enclosed by each one of those geodesic triangles should be that over 8, or pi over 2, which it is. And I'm going to keep that number on the screen. Now, if we analyze these triangles just a little more, you'll notice their angles don't add to 180 degrees. In fact, if we analyze any angle like this one here, it actually is 90 degrees. That would be the case for any one of these angles. So for any one of these triangles, we have 90 plus 90 plus 90, which is 270 degrees. 90 more than a typical triangle on a flat plane. So we can say there's an excess of 90 degrees, or pi over 2 radians. And that excess in radians matches the total curvature enclosed by that geodesic triangle. And it turns out this will in fact always be the case. As in, the total curvature enclosed by any geodesic triangle will always equal the angle excess of that triangle. We just saw it for a sphere that has positive curvature. But for a surface with negative Gaussian curvature, the angles will add to less than 180 degrees, which means there's angle deficit that can be thought of as negative angle excess, which matches that negative curvature enclosed by the triangle. And on a flat surface, the angles will always add to 180 degrees, thus no excess and no Gaussian curvature, since again, we're on a flat surface. But where does Euler's characteristic come into all this? Well, that takes us to something called the Gauss-bonnet theorem. To again kind of oversimplify, this says that the total curvature of a surface, aka the integral of the Gaussian curvature, equals 2 pi times the Euler characteristic of that surface. This theorem is interesting because it links 2 branches of math. Curvature is more of a geometric property that depends on local characteristics like angles or arcs and how the shape is bent in space, while the sum of those is what gives us the total curvature. But the Euler characteristic has to do with the topology of the object, a global property that won't change by those continuous deformations. So geometry and topology, or local and global properties, the Gauss-bonnet theorem links these together in a fairly simplistic way. So for a sphere that has an Euler characteristic of 2, the total curvature by the equation above should be that times 2 pi, or 4 pi, which is exactly what we had just found. And if we deform the sphere into something else, the Euler characteristic and total curvature do not change. Any new regions that don't curve as much now are balanced out by other regions that curve even more. This also means that all the platonic solids have a total curvature of 4 pi, since they have an Euler characteristic of 2 as well. These are flat on their faces but hold all their curvature at the corners. Now, if we look at a cube, you'll notice that the angles at any corner add to 270 degrees. I'm then going to subtract that from 360, which gives us 90 degrees or pi over 2 radians, because this is considered the angle deficit. Unlike the triangles from before, this deficit tells us by how much the angles fail to sum to 360 degrees or 2 pi radians. If we multiply that deficit of pi over 2 at each corner by the 8 corners, we get 4 pi, which is the total curvature of the surface. For a tetrahedron, the angles at any corner add to 180, thus the angle deficit is 180 degrees or pi radians. Then if we multiply that deficit by the 4 corners, we again get 4 pi, the total curvature. This will be the case for the other solids as well, and I just wanted to really highlight that there's this direct relationship between angle deficit, or angle excess, and total curvature. Then if we look back up at the Gauss-bonnet theorem, you'll note that if the Euler characteristic of a surface is 0, like for a torus, then the total curvature must be 0 as well. If we look at a torus, this makes perfect sense. Its outer portion has positive curvature because at any point those principal curvatures both curve outwards. But inside, at some point, you'd have one curve inwards while the other curves outwards, thus negative Gaussian curvature. But as you sum everything up, the positives and negatives will all cancel, giving us a total curvature of 0, just like the Gauss-bonnet theorem says. The most famous application of curvature probably has to do with general relativity and how our universe is curved, but again, you can find all that in the video I'll link below. Now moving on from curvature, as a more random example, Euler's characteristic can be used to prove Pick's theorem, a formula that finds the area of any polygon on a grid of equally spaced points, which is only dependent on the number of points along the boundary and on the interior of the polygon. So the area of this is 15, which you can find by just counting the red and blue dots. Or another example is Euler's characteristic can be used to prove the 5-color theorem, stating that only 5 colors are needed to cover an entire map, such that no two bordering regions have the same color. Although this was surpassed by the 4-color theorem, which is just much harder to prove. Up and Adam did a great detailed video on that, which I'll link below if you want to see the actual proof. And there are so many more examples that I'm just not going to get to due to how long this video already is. But if you guys enjoyed learning about topology and graph theory and Euler's characteristic, then I highly recommend checking out this book, Euler's Gem. Pretty much covers everything I talked about and way more, from the history of Euler's characteristic to knot theory to higher dimensions and so on. So I'll link that below for anyone who's interested. And then for anyone who's looking to learn about, well, anything else from science to technology to history and more, you can head on over to CuriosityStream, the sponsor of today's video. CuriosityStream is a streaming service that hosts thousands of documentaries and nonfiction titles spanning subjects, like I said, such as physics and the universe to technology to nature and so on. If you're like me and love learning about physics and our universe, their series on amazing gravity is one I would definitely recommend. In these videos, you'll see exactly where gravitational waves were first discovered and how space-time doesn't just curve, but it can ripple. You'll learn more about Einstein's general theory of relativity and the consequences that come from the underlying curvature of our universe. They cover some of the latest theories that are helping us understand the cosmos, groundbreaking experiments, and of course, plenty more. The service is available on a variety of platforms worldwide, including Roku, Android, Xbox One, Amazon Fire, Apple TV, and more, and it only comes out to $2.99 per month. Plus, if you go to curiositystream.com/majorprep or click the link below and use the promo code MAJORPREP, you'll get your first month's membership completely free, so no risk in just giving it a try. This gives you unlimited access to top documentaries and nonfiction series that I know many of you will find very interesting, so again, links are below, and with that, I'm going to end that video there. If you guys enjoyed, be sure to like and subscribe. Don't forget to follow me on Twitter and join the Major Prep Facebook group for updates on everything. Hit the bell if you're not being notified, and I'll see you all in the next video.